Hello, everyone. Welcome to WT Squared, and thank you very much for joining us in this session. My name is Amber. I'm with VMware as an escalation engineer, and I was part of the program committee for the technical track at this conference. I get the pleasure to introduce our speaker in this session, Jiaqi Liu. She is a data scientist with Capital One, working on consumer-facing data, and her work revolves around using big data tools and machine learning algorithms to gain insights from bank and credit card data. She works with large-scale data platforms and enjoys seeing challenges in consolidating the science and engineering part of data-driven work. Please join me in welcoming Jiaqi.
Thank you, and thank you for an amazing talk with Rashmi earlier in the session. If you missed it, she's in the audience, you can follow up with her afterwards. My talk is going to be titled Velocity, Volume, and Veracity. And if you're in the data science space, you probably heard that those three terms mentioned before. They're known as the 3 V's. I'll delve deeper into them later on. But it's also about leveraging DevOps culture within data science. And so I'm going to talk a little bit more about myself and how I fell into data science. And I'll talk a little bit about what data science is and what DevOps culture is, and then how those two things go together. Happy to take questions at any point during the talk. I know it's a small audience, so I want to keep this session intimate and open. So about myself, like Amber said, I'm a data scientist with Capital One. Capital One is a bank and a credit card company. What my team does is slightly different from traditional fintech. We try to do alternative things with our financial data and provide different experiences for our customers. To give you an example, for instance, one of the features that my team launched is this restaurant recommender system in our Capital One mobile app that sort of recommends you restaurants based on how Capital One customers spend, which is very different from what you would imagine a financial company to be doing. So I'm pretty blessed to have a job that's a little bit unique in a really well-funded company. So it's like being a startup within a large company. I am a Python developer. Yay. Any other Python developers in the crowd? Awesome. So I had a hard time identifying myself as a Python developer. I started out with Java, strongly typed languages, and I did some JavaScript as well. And then within data science, you tend to have a lot of Python developers because the community and the open source community is just so strong in terms of the modeling tools there. So at first I had a really hard time identifying myself as a Python developer because I used to look down on loosely typed languages. But now I am very proud to say that I am a Python developer, and I really adore the community. It's just so wonderful and open. And it's a great community to be a woman in tech as well. They're so supportive. I'm based out of New York. I am active in the New York chapter of Women Who Code. Kate is in the audience, is also from the New York chapter of Women Who Code. Sorry to put her on the spot. So we're actually doing a lightning talk series in April. So if you happen to be in New York, feel free to check that out. Did you have a question? Okay. Cool. So diving into the talk, what exactly is data science? This seems to be a really ambiguous topic because depending on what company you are talking to, what organization you're talking to, you might get a different sense of what data science is. Some could argue that data science is relatively new term or new job, but really it's been around for a while, and it's just taken on a new role, especially with big data tools becoming so much more accessible these days. So a lot of the concepts that are prominent in data science today, such as machine learning, deep learning, have been around for a couple of decades, but the hardware to support it have not. So for instance, big data, the whole concept has been around for a long time. Distributed computing has been around for a long time. But now those ideas are not only easily accessible, but easily implemented. And anybody could essentially go and rent a Hadoop cluster on the cloud and start to do big data or start to do deep learning. And it's much more accessible. So companies are starting to do it more. And data science as a job has started to grow a lot. But that said, there's still a lot of ambiguity around what data science is. And it's kind of this mesh of statistics, analysis, behavioral science, visualization, and it's very, very broad right now. I can tell you a little bit about what data science means to me. So I come from a theoretical computer science background. So I studied P, not NP, and I aspired to solve P, not NP. Granted, we know how difficult that is. And some of the things I studied is really around algorithms and how do you scale algorithms, how do you optimize algorithms. How that fits into data science is a little bit, it's kind of ambivalent, right? Like there's algorithms in every part of computer science. I did not study statistics, although now I wish I had because I do so much of it. And what I also studied at school, in addition to computer science and theoretical computer science, is actually history and human behavior and politics. And that's what sort of brought me to data science, is this combination of the humanities and computer science. So within data science work, it becomes really interesting when you look at the data and then look at customer behavior and see how numbers start to reflect the behavior of customers, the insights you get. Something that my team is super passionate about is being able to look at the numbers and understand someone's situation or someone's where someone is in life, and being able to use those insights to help them better their financial wealth. So that's one aspect of data science, and I have coworkers who come from various backgrounds. I have coworkers who used to be astrophysicists. I have a coworker who used to be a theologist, and it's this combination of like interdisciplinary studies that allow us to do what we do at work and allow us to innovate on the data front. So going forward, if you seeing data science job recs out there or seeing talks about data science, you probably have seen a diagram like this, where data science is at the intersection between strong programming skills, math and statistical knowledge, and the subject matter expertise, which can also be known as business insights. And you have to have all of these things to become a data scientist. In reality, no one has all of these skill sets. It is incredibly hard to hire someone who is super great at programming, excellent at math and statistics, and also a great communicator and great at business insights. And that is true for most jobs. I've seen a diagram like this for design jobs, actually, where designers also have to meet some trifecta of skill sets. So in reality, it's incredibly difficult to hire someone who has all of these skills, and we call those people unicorns. I'm going to use the term unicorns more than once in my talk, so I apologize for being sort of on that term. But anyway, I, for one, definitely do not have all of these skill sets, or at least I don't think I do, although some might say that I should say that I have all of these skill sets because I am a data scientist and therefore I am all of these things. But what you actually want to do is build a team that has strong skill sets in all of these in order to ship data products, and also to hone these skill sets over time. So I would argue that a seasoned data scientist might not have had discipline training in all these skill sets, but they have really good intuition around programming and architecture, even if they're more of a statistician, or they have really good business intuition, even if they're actually an engineering manager. So I'm pretty fortunate to be working with people who are like that and to work in a team where collectively we can rely on each other to sort of meet the three skills that you need to have a functioning data science team. So In 2012, I believe, DJ Patel and Thomas Davenport wrote an article in the Harvard Business Review about data science as the sexiest job of the century. And in this quote, they say, if your organization stores multiple petabytes of data, if the information most critical to your business resides in forms other than rows and columns of numbers, or if answering your biggest question would involve a mashup of several analytical efforts, you've got a big data opportunity. And this kind of goes back to how nowadays data is so prevalent now. There's a lot of information. It's really hard to make sense of it all. And they're no longer in traditional forms of maybe just relational tables. It comes in streams of log data, or it comes in streams of clickstream data from users, or it comes from open-ended feedback or geolocation data from mobiles. It becomes really challenging to figure out what do you do with all of that data. And then there's a separate problem of, okay, you have this much data and you figure something that you can do with it, but you need this other component of data to get to where you want to, in which case, how do you go about collecting more data? And what exactly is a big data effort? So this is definitely a challenge for a lot of organizations. My own included is we have so much data, and what do we do with the data that we have, and what other data do we need in order to truly generate valuable insights for the business? Because at the end of the day, data science is still about driving the business forward. So this brings me to the types of data science work that there are. It's kind of tricky, but from my perspective, and feel free to disagree with me, there's a spectrum of data science work. On the far end is the research-oriented work. So if you can think of this almost as pure machine learning research, or given a collective set of data, pure research on what you can do with that data. And then on the other end is the product work. So using the data and the research that you've done to build a product. So for instance, the restaurant recommender that my team has built, that would be considered a data product. Or if you use Waze when you drive, having that insight to know how traffic is flowing based on users, that's a data product. And it's a little bit hard for teams, for individuals even, to balance between research projects and data products. For instance, if you are constantly working on research projects within a company and none of your code ever goes into production, none of your work ever ends up being consumer facing, it can get really frustrating as a data scientist. And in addition, you're not exactly sure if you're providing value for your company, because it's really hard to measure the immediate impact of research projects. That being said, research projects are incredibly important, without which innovation cannot occur. So there needs to be some investment in data research projects. And then on the other hand, with data products, it becomes really hard for data scientists, because most data scientists are so new to software engineering and software development, to build data products that are sustainable and scalable. So I'll tell a broader story on this later, but for me at least, when I used to work on a team that was mainly focused on doing research and building prototypes. And it gets really easy to fall into this habit of, hey, I built this model, it works great on my computer, and it works great on the dev instance, hand it off to somebody else, it's their problem now. But that's not sustainable if you want to build a data product that actually lasts. Okay. And this brings me to another point from from the Harvard Business Review article is that data scientists, just like other developers and engineers, really just want to build things. With the type of research work that happens, it's very common to see data scientists almost as advisors or consultants, someone who comes in, crunch the data, and then gives a recommendation at the end. That definitely happens in certain organizations, but if you need a skill set like that, that's maybe a product analyst role or a data analyst role, versus data scientists really want to eventually get to build those data products, and they do want to program really heavily and be able to ship their product. So this goes into this maker and builder culture idea where everyone should be able to own a product lifecycle from end to end, even data scientists. So in talking about data science work, I just want to give an example of sort of what it is when I say research work, or rather exploratory work. So this is an IPython Notebook. An IPython Notebook is super great for prototyping and also for making presentations. It's commonly used by data scientists to sort of quickly analyze data and quickly make plots. I like to think of it as the modern Excel, because I haven't used Excel in a very long time, and I'm much more comfortable using IPython than Excel. It is, however, not production code. You can't take a IPython notebook and deploy it onto a server. You can take the code on it, but you can't deploy an IPython notebook. Although actually you can, in fact, deploy IPython notebooks because they're hosted on a web server, and you can actually symlink your way to production. But that's not really what a product is about. And it's pretty common practice on a lot of teams for data scientists to do all of their development work in this kind of environment, in their local environment, essentially. And then they'll hand off the code to a team of engineers who would then implement it. So that's pretty common practice. And up until recently, that's how my team operated, is data scientists would turn away some code and prototype, and it'll work great locally, hand it off and all the documentation to a team of engineers who would then implement it in the cloud or on the server. So this brings me to my next slide, which is that's not the same as production, and that is not the same as building an end-to-end application. So in this talk, I hope to focus more around why it's not just a technical problem to be able to ship data products. It's not just about taking code and putting it into production, but it's also a cultural problem around how do we build cross-functional teams that care about the end-to-end process, and how does engineering, data science, and product all get involved in the beginning to build these awesome data products and work on these awesome research projects. So this is where DevOps culture comes in, and Rashmi had talked on it earlier as well, so I'm super glad to elaborate more on it, I guess. But before I talked about DevOps, I have a little story to tell, and I'm going to title this story "The Little Pipeline That Could." Yay. So if you work in the data space, you probably heard of a data pipeline. Essentially what happens is you have some process that takes as input some source of data. It does a MapReduce job or some sort of ETL process or ETL process, and then it feeds it into another process which just does something else, and then it feeds it into a database as output, and then you can have a API that surfaces the result of that database. This is pretty common practice, and you'll see variations of this throughout data work. Process A could be cleaning up the data to be ready for process B, which could be a machine learning algorithm, which could then spit out as a result to database A, which can then be served to a client. So my team built a data process like this. And then we realized that we wanted to add more features. So the little pipeline grew into a slightly more complicated pipeline where process A had 2 different outputs that spit out to 2 other processes. And then that ended up being the input of one process and goes into a database. And then we realized that, hey, like not only do we want even more features, but we actually want to collect more metrics about our own system. So in addition to just spitting out an output, we're going to collect metrics around that output and make some analysis based on that, just because we're interested. And eventually, the little pipeline that could grew into this big pipeline with multiple sources of inputs, multiple processes, and that output to different things. And it got very convoluted, which is fine until one day, one of the processes started to stall out. And what this meant was its dependents would fail because they didn't get the input they were expecting. And what this meant was things in that, essentially that branch of the pipeline would start to fail. Okay, that's fine. If you have a bug in your large software system, you go and you deploy a fix. So that's exactly what the team did, is they fixed the process and everything was back to normal again. And that's super awesome. Until some other part of it starts to fail, and then a lot of it started to fail, and it got more and more complicated to fix things. When you have a large system, essentially a monolithic architecture, it becomes harder and harder to deploy new features and harder to fix things. And even worse, when your teammates start to offboard to other projects, when you have new people on board to your project, you start to lose a lot of that domain knowledge as well. So some really weird tricks that people were doing to fix certain parts of the pipeline now have left the company or have left to a different project. And you start to lose some of that domain knowledge, you start to lose some of the original code, and it gets very confusing, and it just becomes impossible to fix, becomes impossible to add to, and you can't deploy new features. If the data changes in any way, the pipeline breaks, and it becomes a very fragile process. So essentially, we were hardworking plumbers working on our pipeline, and it sort of fell apart, and we were overwhelmed by the flooding waters. That is our monolithic architecture with so many interdependencies. So how do you avoid all of this? How do you fix this? You do want to move away from this monolithic architecture of interdependencies. But what we learned from building that giant pipeline was exactly what our SLAs were, exactly what we needed to see as our output, and exactly what kind of features we wish we had. So we got a wonderful wish list out of that experience that we can leverage to build our individual microservices now. But we also want to be able to have a robust way to roll back the code and the platform. And I sort of want to emphasize rolling back code and platform. I think we all understand the importance of version control for our code and using GitHub, and that's pretty standard in terms of in the industry and in terms of data science work as well. But a lot of the issues that came up with our pipeline ended up being that certain amount of memory allocation on the infrastructure wasn't correct, or the certain way that we organized the distributed system just wasn't working great, or we tried to add a node to our Hadoop cluster and it wouldn't take. So being able to version control the platform is just as important as versioning the code. And in addition to all of that, having well-documented code and also having knowledge transfers so that knowledge of how your software system works doesn't just leave when your team members leave. So I want to bring up this book called The Phoenix Project. How many of you have heard of it or read it before? So it's actually a fictional book, but it's about IT and DevOps. And it has a very similar story to what happened to my team. I'm not going to spoil the story, but essentially, in a large corporation, that could be any corporation, they were having trouble deploying new code and meeting their business expectations because there were so many bugs to fix and so many emergencies that came up all the time. In addition to having specific people who were bottlenecks or who were just the core people who had all the domain knowledge and lack of documentation, lack of structure. So they talk in the book, they talk a lot about Agile and Kanban. They also talk about DevOps culture and things like that. But what resonated with me a lot when I read this book is at the end, they have this section around like real world stories. And they talk about how people think that those companies that have good DevOps culture are all unicorns. And this is my second time using the word unicorn for this presentation in different contexts. And those unicorns tend to be startups or companies like Facebook and Amazon and Netflix. And they just have it all figured out. But this is not the case. In fact, all of those companies probably at some point started out as horses. And in fact, unicorns are just horses with horns. And they actually give a lot of case studies around how Netflix actually had to figure out its own DevOps needs once it got really big. And Netflix is very famous for its chaos monkey principle, where they deploy this chaos monkey into both QA and production that sort of destroys everything to make sure that their system is resilient. In addition, there's a case study around LinkedIn and how LinkedIn had to have a code freeze because it became so hard to develop new features and they started to have to adopt DevOps culture. So it's pretty interesting and inspirational for me to hear that, hey, my team is not the only one with these kind of problems. In fact, this is a very common industry problem. And each project team, each company has to sort of deal with it on its own way, but it's not unprecedented. So one aspect of it is technical debt around, if you, I don't know, maybe you were in a rush to deploy a feature and you coded something poorly or you forgot to write tests or something, and those kind of technical debt need to be addressed in addition to deploying new features. Having bottlenecks on projects because you're constantly putting out fires and constantly putting out fixes before you can roll out new features. Or just having a hard time shipping new features in general because your developers, again, are so focused on fixing issues as opposed to spending their time working on new features. So something that maybe if you are a developer, you might want to ask yourself is, how much of your time do you spend working on new features as opposed to fixing bugs or doing production support tasks? So when I was working on my large pipeline project, I was spending up to 50% of my week working on production support, which meant that I didn't have a lot of time to actually work on real new features that we wanted to implement. Okay. So what is DevOps then? Like I mentioned, DevOps is not just a technical practice, but also a organizational culture. I took this from the 2016 State of DevOps report by Puppet Labs. And in it, they talk about how high-performing organizations spend 22% less time on unplanned work and rework. So essentially, 2% less time on production support or redoing the work that they supposedly already have completed. In addition, this means that those high-performing organizations have 29% more time on new work and working on new features, and spend 50% less time working on security issues, which is pretty empowering. And in addition to that, high performers have a much faster mean time to recover, and that is also really empowering for your SLAs. Actually don't work on projects that require me to have a pager. That's one of the benefits of working on non-financial projects when you're in a large bank. But for typical software engineers, you do have to understand that, hey, if something breaks, you have clients that are depending on it and there are consequences. So it's very important to recover as quickly as possible. So I'm going to talk a little bit about some of the best practices within software engineering. This is not what this talk is about, so I'm going to sort of cruise over these ideas, and if you have questions later, I'd be happy to address them. But these are just sort of the foundations of DevOps and best practices that lay the groundwork for many different kind of projects and not just data science projects. And after this, I'll talk more detail on what kind of particular practices you do need for data science projects. So infrastructure as code is one important aspect. That's the logo to Terraform. So I sort of mentioned earlier that it becomes really pivotal to be able to roll back your platform in addition to your code. And the best way to do that is to write up your infrastructure as code. Rashmi had touched on this as well. CI/CD, meaning continuous integration, continuous deployment. So you should be trying to deploy as many times as possible because you can always roll back if something doesn't go well or if you change your mind about a new feature. So this is a logo for Jenkins, which is a great CI/CD tool. Automation, containerization. So containerization sort of goes hand in hand, I think, with infrastructure as code, so that you can preserve your environment across different parts. So dev and QA should be identical to production because how are you supposed to test your application works the same in QA as in production. Test-driven development / behavior-driven development. So the idea that you should be writing unit tests or integration tests before, have your tests fail, and then write the code that will allow those tests to pass. Behavior-driven development is more centered around UI and UX. So I have Jasmine up there, which is a testing tool for JavaScript, and PyTest is a testing tool for Python. So this goes back regarding the cultural part of DevOps, is that DevOps should be everybody's responsibility. It shouldn't just be one developer or one data scientist working on production issues, but rather it's the product team's responsibility to worry about how is their project going to go into production. That is something that the team should be thinking about from the very get-go. So how do you go about doing that? How do you go about ensuring that you are able to leverage DevOps culture when you're shipping your product? And that's really around setting clear goals and deliverables from the very start and defining what production means for your data science work. So to give you an example, in marketing, typically you do a lot of research with data and you sort of try to target who it is that you are trying to market to and what your goal is. Within Capital One, because we do a lot of direct mail campaigns, it's very possible that your production work is actually just a final list of here are the people that we want to mail things to, which is very, very different from, I imagine, how Facebook would do advertising, where your production is actually more of a service that reflects, hey, these people meet this demographic and should be served these ads. And it's much more of a reactive real-time framework as opposed to in the Capital One direct mail campaign, a very batch structure where it's, hey, maybe we're sending out a batch of mail this time, we need a list now, as opposed to a constant reactive framework. So I want to address the volume, velocity, and veracity part of this talk now. And I kind of wanted to bring this up because it's very common in data science to use these three phrases, and they mean exactly what they mean. Volume as in big data, velocity as in fast data, reactive stream architectures, and veracity as in the accuracy of maybe both your data sets, but also the assumptions you're making and the output of your model. So veracity is a little bit more complicated than the other two topics. To give an example, in terms of volume and maybe even velocity, because of how easily accessible Hadoop and distributed computing are these days, you can actually download all the books on Project Gutenberg and count the frequency of each word using a distributed system. This is essentially the hello world to data science, is performing word count on a large data set. So this is really great and actually incredibly powerful, but also a little bit scary, because with the ability to process big data, in traditional statistics, you would, let's say you would find some general picture of a data set by sampling, by randomly sampling and then generating a average on the random sample or a standard deviation. That would be your broad picture of the data set. That those would be the assumptions that you work with. But now, instead of just sampling, you can actually just calculate the mean and variance for the entire data set as its source of truth. So this brings data scientists to a part where they get really confident about their data because, hey, I didn't sample to get these results. I got the results off the entire data set. Doesn't that mean that it's more accurate? But no, it's not, because it becomes harder to see all the outliers and the full picture because the smaller subsets and smaller classes and smaller outliers start to get lost within the broader data set. So it's still very tricky to work with big data, even though it's definitely a huge leverage in terms of being able to analyze the entire data set as it is without sampling. I have another story on sort of the trickiness of veracity, which is this XKCD comic. And I firmly believe that you can't have a tech talk without an XKCD comic. Is this data visualization example where 3 different topics are plotted on a map, and they're all about population. So naturally, it seems like, hey, the business implications are obvious. All these 3 things are related, and you should totally be advertising furry pornography to subscribers of Martha Stewart Living, because it's clearly they all live in the same area. But really, these are just geographic profile maps, which also happens to be population maps, which are denser on the coast. And this brings up the interesting point of when you're working with data, sometimes you have to account for a lot of different aspects, in this case, population. And the best way to go about this here is to normalize your data based on population. But it's also really tricky to sort of understand your analysis, because none of it is black and white. It's all set within some context and some bigger picture, and you have to be very wary of that as a data scientist or as an analyst in general. I have another interesting tale. In 2012, Boston launched the Street Bump mobile app to help measure where there are potholes within the city. Analysis of the data they collected from this app found that all the potholes, or not all the, a lot of the potholes were in affluent neighborhoods. And this was obviously very interesting, but it's also due to the fact that the users of those mobile apps tended to live in affluent neighborhoods, because people who own smartphones tend to be in affluent neighborhoods. And this sort of accounts for another aspect of Veracity is, yes, you can analyze all of that data. You have the tools to collect that data, but you have to understand where some of the biases are when you're collecting the data. So this isn't even in terms of inaccuracy in the analysis. This is a bias in the collection method, which is very, very tricky to sort of realize these things. This brings me to my next point, which is that big data cannot replace domain knowledge, because some of the weird quirks and outliers, those come from understanding not just the data and statistics part of it, but the behavior and the social aspects of what you're trying to study. Okay, so I've talked a little about sort of the trickiness of data science. And I want to go back to talking about DevOps and what DevOps for data science means. It's about having some way of validating your data, having feedback loops, either from users or from your own system, and having analytics as a software. So model validation and feedback loops. This is something that I think a lot of teams are struggling with now, is how do you test data science outputs and how do you test non-deterministic algorithms? Because oftentimes a machine learning algorithm is a non-deterministic algorithm and the output changes each time. So you can't exactly just write a unit test to make sure that, hey, this input should always have this output, because maybe that's not what your algorithm is supposed to be doing. Let's see. Yeah, so it becomes very tricky to have some way of providing a feedback loop for your machine learning model, or having some way of checking it, and having some way of monitoring the outputs of your model, because maybe you are willing to tolerate inaccuracies occasionally, but you at least want to know about them. Okay, so if you start to think about that, then doesn't that sound like a data science problem in itself? So you're talking about monitoring, validating data, checking data. That seems to like it can be solved with data science. So that's exactly what it is. Actually, it's not just a data science problem, but it's a big data problem. In fact, you can probably build an algorithm that checks the validity of your other machine learning algorithm, and you can use types of anomaly detection to figure out if your data collection or if your data integrity has been compromised. And obviously this starts to get bigger and bigger because now you have all these other algorithms that you have to check for. So this sort of brings me back to velocity, volume, and veracity, is that you want to make sure you have the right architecture to feed that, to have that feedback loop, and to be able to do certain checks on your data and your output if you need to. And you also want to be able to leverage volume to maintain veracity. So with big data, there's a lot more that you can account for, a lot more you can check for. But with real-time systems, with velocity, maybe you can't always aggregate those responses in time. So you want to be able to leverage big data systems to do that. This right here is called a lift or a ROC curve or a lift chart. And essentially on the x-axis is the false positive rate, on the y-axis is the true positive rate. And what a good model is basically something that has the greatest area under the curve. And in this example, there's a relatively bad model, a relatively good model, and a great model. And what I'm trying to say here is you kind of have to know what you're willing to sacrifice and what you're prioritizing. So maybe the great model here outperforms everything, but it is slow, or it needs a lot more features than the other models. Then if you're building a really fast real-time system, maybe you can't afford that. versus you'll just settle for the good model, which is a lot faster, but maybe it isn't as accurate. So there's this constant trade-off within data science of what are you striving for? What is your goal? And how does the system help you achieve that? And what are your trade-offs? What are you willing to give up in order to achieve this other thing that maybe will help you more in the long run? So aside from model validation and feedback loops, I also mentioned analytics as software. So having this microservices architecture, having your models instead of big pipelines to be APIs, having reactive programming, and having a real-time and batch architecture that can feed into each other to provide a feedback loop are all really critical things. So I'm going to talk individually about all of those. So in a microservices architecture, you can have an offline training of supervised learning models. Maybe you have an endpoint that says input all your training data here, and this will train the models. And then you'll have another endpoint that will allow the user to put in their input, and you'll return with the output. A common example of this is actually if you've used, I think Google has a great image recognition API. So just clarify, if you've used those are essentially image recognition as an API. My team builds a machine learning API that does a fuzzy search on transaction information. So we train all of that offline. We don't have an endpoint to allow users to train the data because we train it on our own data set. And we take transactions one at a time and return the fuzzy search results that we generate with it. Microservices should be easy to integrate with other services or applications. So the goal of my team building this machine learning model as an API is that different parts of the company, different parts of the business that might want to do the fuzzy search will no longer need to embed it into their own code. Instead, they can just call our API. And they don't even need to know how to train the algorithm or how the algorithm works. All of that is obfuscated. Reactive programming is it's a pretty commonly known concept. I got this image from the Reactive Manifesto, and if you want to read the entire manifesto, it's available online. So in terms of how this relates to data, part of reactive programming is this event-driven idea where as an event happens, you respond to it. And in a lot of data science today, there's a sense of real-time processes and stream processes, and you want to be able to respond to events as quickly as possible. So an example I can give you there is using, let's say, anomaly detection to detect data quality as it comes in from whatever source it is. You want to be able to reject poor quality data as it comes in. So you want to have event-driven behavior, and you want to be fault tolerant on that. Okay. What about online learning or feedback loops? So I've talked a little bit about offline training, which is essentially where gathering a batch of training data and giving it to the model before it starts to process data. What about real-time training? How does that work in data science? And this brings me to the unified batch and stream architecture, also known as the Lambda Architecture. So the people who made Kafka, which started from LinkedIn and became its own company called Confluent, sort of came up with this Lambda architecture, which is where you have a stream process, but you also have a corresponding batch process for all the batch work that you might need to do. In this example, let's say Kafka is feeding in real-time input to some sort of stream process, and that's serving an application. Maybe the historical part of either user behavior from the application or historical data collected feeds into this batch process that generates insights and learning and training data that gets fed back into the stream process so that it can learn on demand and perform better. So this is sort of the Lambda architecture of having both a batch process and a real-time process. It's great in the sense that it does, in fact, fulfill the volume, veracity, and velocity aspects of data science, but it gets very tricky because you're essentially maintaining two different platforms. You have a stream platform and a batch platform, and it can become really hard to maintain code and infrastructure for both. And so again, the folks from Confluent sort of came up with this idea of the kappa architecture, which is let's just do away with the batch process altogether, because a batch process is essentially a stream that starts at a historical date. So what is the point of having a batch process when you can essentially rewind your stream so that it processes historical data anyway? And that sort of reduces the complexity of a unified architecture. It's hard to say like which one is better. There's pros and cons to both, and my team frankly works with the Lambda architecture a lot more often than we do with kappa architecture, just because we're not as familiar, and there's certain things that's organically and easier to do with batch processing. But that's sort of ends my talk, and I kind of want to end with the note that with data science, it's important to account for the different types of data science work and sort of define what production means to the system. But also always keeping in the back of your mind, even if you're working on a research project, what production is to you and your team and how you plan on getting there. And I just kind of want to end on the thing on architecture and algorithms, and sort of tying it back to going into production is thinking about, as your program gets bigger, as your software gets more complicated, what kind of architecture you want to go with and what kind of algorithms you want to work with to avoid things like constant downtime, to avoid things like really difficult to fix bugs, or to avoid having to do a lot of the work over again to sort of avoid technical debt. I have some references here. The slide will be shared out, so feel free to, you'll have access to all the materials I mentioned in the talk, and that is it for me. So I'm opening the floor up to questions.
We have a few minutes for like about 5 or so, if any questions there.
You mentioned shopping patterns, and
yeah.
You can find more, and that's the app that you're working on is kind of outside the finance realm.
Yeah.
Are there any other cool things that you can talk about that you're creating at this point?
Ooh, I can't really think of anything. But so my team is pretty flexible on working around interesting ideas. Actually, something that I've explored in the past, which didn't work out, is building this idea of sort of personal advisor almost around like, can I afford that when I'm out shopping? Essentially, it's the idea of trying to like calculate based on your spend and your bank data, how much are you willing to like tolerate in terms of like excessive spending? And that's sort of an interesting question that is surprisingly hard to answer because everyone is just so different. It goes back to the behavioral sciences of it all, is that it's really hard to predict if someone is more, can they like spend this much this week, and do they have other things they should be accounting for? Are they more tolerant in general of like financial risks at this point in their life, or are they not, and things like that?
It's needed. I know Susie Orman does that with her own mind out.
Yeah. Yeah. Yeah, it's so
good for everybody.
Yeah, it's so interesting how like everyone's able to do it in their heads, but it's really hard to like create an algorithm that sort of solves it. Any other questions? Yes.
You mentioned cross-team effort for DevOps. How do you go about kind of building that culture across teams that may not work directly with each other?
Yeah, that's really tricky. So I've been fortunate in the sense that my team is we report to different people organizationally, but we are a product team. We very much consider ourselves a product team. So we've been working together on the start of our project, and we sort of all agreed on this at the very start of our project. But it does get very hard if you, let's say you're working on a project with a team and you already agreed on these kind of like, this is your coding standard on the project. This is your DevOps culture. This is what you agreed on. And then suddenly you also have to work with another team who might have a different set of standards. It does get really hard to sort of blend all of that together. Something that I know Capital One has been trying to do is have a company-wide DevOps culture, or like a manifesto coming down from like the CIO, because that makes it a lot easier for everyone to get on board and sort of agree on things. But it is very tricky to sort of leverage this transformation thought leadership from like a junior developer standpoint. But then again, sort of part of this conference is inspiring you to be a leader and be a thought leader, I guess. Yeah. Cool. Yeah.
Okay, well, if there's no more questions, thank you very much. Thank you
for
this session.